Thank you very much. I want to talk about the analysis of temperature depth profiles. The topic came up a couple of times already this morning. I just here on the first slide present you a few examples from literature. If we start on the left-hand side, many of you are probably familiar with this kind of step function here. I think the next talk will be a bit more on the stratification, so we'll see a lot of those. The topic for me today is less on the specific profile, but presenting you some work we did on the data-driven analysis of those profiles. So detecting such a kind of steep change is not so difficult, but if we look at the middle example, right, there is a lot of things going on in the different profiles, and you might want to see how things change over time if you take the profile multiple times, like in this example, or also just see what the if you have different mine shafts, how they behave differently to each other. And we also want to raise a bit of awareness is about the method and principle. You see this on the first example here on the left-hand side, where they nicely show you differences in whether you lower your sensor or if you put your sensor up, that can affect your data, first of all, and then potentially your data analysis. So we want to try to get that more on a bit statistically robust approach in terms of data analysis. And just as a brain teaser on the right-hand side, yes, this year is a mining conference, but we're facing the same problem in other situations in hydrogeology. If we look, for example, at deep groundwater wells. So this here on the right is an example from the Netherlands with a 100 meter, 150 meter water well, where you would try to identify with your geological profile, for example, where your well is cutting different aquifer systems and determine how flow is behaving. Very similar, like we have that in the mine, where we might want to see where water is entering or leaving our galleries. So the motivation for us, very general, is that these temperature profiles is very common to take because it's easy, it's quick, it's usually very cost effective. But then the analysis of those ones, with respect to geology, hydraulics, this is a lot left to individual interpretation and this expert knowledge. So our goal was to enable a data-driven approach. So taking a bit out the subjectivity out of the equation, increasing reproducibility by enabling this analysis based on quantitative criteria, while still allowing high-grade flexibility. So still allowing the user to put the focus where they want to have the focus on. And if you want to look onto small segments in detail, or you really want to look on 800 meters of depth profile and just want to have a coarse scale, right, still allowing this flexibility. The methodology we chose was developing a MATLAB toolbox, which is a fancy word for a collection of functions and a main file that kind of puts them in order, right? Covering the pre-processing of the signals as well as then the individual signal analysis, with always having this statistically robust handling in mind, but of course by this method gaining a huge benefit in terms of speed and reproducibility, and also in terms of transparency of how the processing was done. Focus, I think, of this conference here is a bit more on applications, so I skip you all the algorithmic parts and focus a bit more on what can be done with the toolbox based on a real case scenario from a mine that we're used to. So the test site I'm here presenting you is an old ore mine in Western Germany, in Bad Ems. So if we look at the German map, we are a bit south of Cologne, quite central Western Germany. The mine closed down in 1945, matching to the date today. So due to the end of the war and ongoing conflict, and the mine was flooded uncontrolled after that. And now the water level has reached an running galleries, what we call the Stadtstollen. And this is quite close to the city center, as you can see here. We have 2 shafts going down in the mine up to 15 galleries below this Stadtstollen level. And you see the geometry of the mine itself is rather complex with a lot of different galleries, pumping facilities, and so on, and then the excavated and refilled areas along the hallway. What also makes this site specifically interesting for us is that in the city itself, we have thermal springs, so just out of the map here in the south. There are multiple thermal springs, and it's known that these thermal springs also discharge into the mine. So this gives us a mine water discharge temperature of 26 degrees Celsius, which is also used currently for geothermal purposes. And the city would like, of course, to expand the usage of that. But for this, and that's how we come to the analysis of temperature profiles, right? We want to know how is the water flowing, where is the heat coming from, and can we characterize the mine in some way. So we do have access to the shaft. As you can see here, the mine itself is also connected to more mining activity in the area. So in the subsurface, there are hydraulic connectivities through mining structures to other parts. To give you a bit more of an cut now of a profile through those different mines. So I will mainly talk about the mine Neuhoffnung and the Weidmann Schacht, which is the longest profile we can take, with almost 800 meters of water hat. Next to it, we have another shaft which we can measure up to a specific depth. And then there's collapse workings in the shaft, so we can't lower the profile lower or sensor lower. We have another profile over here, and the other big part of the mine, the so-called Pfingstwiese. And we do have some information from the very small shallow mine in between, Fallenberg. We don't have a full profile there, which we analyzed, but we do have some information, so we know it's very comparably cold, so 10 degrees, 12 degrees groundwater, and it's very quickly reacting to precipitation, so it's very low mineralized as well. Now, what you see here is the raw data. Okay, so in plaque, that would be our properly measured descent profile. So we lower the sensor quite slowly, and then you see you have the red line, that's the ascent then, which was done with the speed 3 times the rate of ascent compared to the descent. So you see the sensor is not picking up a few signals we detected on the way down, because if you go faster, also upway upwards, the flow to the sensor changes, and the temperature sensor needs an amount of time to equilibrate to the surrounding. Right, so if you lower or speed up your ascent, then you get less signals. What you also see is along the whole, almost 800 meters depth profile, we only got an increase of roughly half a degree Celsius. That was very little, which is caused by the thermal springs, so everything is very warm in principle. But it questioned us, like, okay, what kind of signal can we actually measure with this little value range? And we used a surprisingly expensive temperature sensor from deep sea equipment to measure that. And well, when you do these profiling, right, you always have positions of stationarity. You just insert the probe into the water, you give it some time, and then you lower it, and then you have a point of return at the bottom, right? And we looked for those kind of stationary positions in our profile, and you see we did a lot of measurements, and so we just statistically evaluate, okay, what is the accuracy or the natural variation we have if we're not changing the position of our sensor, right? So the problem in data analysis is with these temperature profiles, you have a dynamic measurement in a dynamic system. So we took out the dynamic of lowering the sensor, just look at the stationary position to get a statistical evaluation. And you see we have variations around the third digit behind the comma, behind the dot, sorry, for the temperature. So we do have some feeling now for the accuracy that we can interpret or not. And based on that analysis, right, you can look at something like a 3 sigma noise level, determine outliers and so on. But this is part of the pre-processing, very much. With this, then we feed a segmentation algorithm. So what you see on the left-hand side, the first picture, you see the same profile again I just showed you before, and now you see the colored backgrounds. That's different segments which the algorithm detected, and I gave you in orange the different mine galleries. So whenever a gallery connects to the shaft, and this segmentation, and this is the strong side of our algorithm, you can do this segmentation based on different properties. What I show you here is hopefully the most trivial one to understand. It's based on the slope, so very much on the thermal gradient. And the algorithm looks for when does this gradient changes, and keeps as the segments points that have the lowest, or that can be best described by one term gradient. And in the interpretation, you will see that, for example, some segments very nicely agree with connections to the shaft. So we can think of what does this mean, what changes there, maybe geometrically, what changes there hydraulically from inflow to outflow, part of that. What you see in the next picture is the same, or the matching part here. You just see the slope, so the degree Celsius per meter for each of those segments. And for example, you can see that we have a few segments along the profile where we actually have a negative slope, so our water gets cooler. And now then we can raise the question in the context. Okay, what does it mean? How does water becomes cooler in such a system? So we have more heat loss. Do we have cold water inflow? How can we relate that?
Thomas, 4 minutes.
Yeah, thank you. So in comparison, instead of the slope, you can also look at, for example, the heat square. So we measure how well does my data can actually be described by a linear trend. So for example, if I have a little variation from this linear trend, then this might indicate from a turbulent flow or other things. You can also do a segmentation here on the right-hand side based on noise, just simply how much is my signal noisy, rough in the signal, and you get a bit different segmentation. Right? So you see this one much more than the other one aligns with the different galleries. So it seems that always when there is a gallery connected to the shaft, there is a change in my noise signal. And with all that, and this is the same image I showed before, but now with some interpretation, right? We try to come up, okay, how can we use this to determine water inflow and simply the hydraulics in the mine? So obviously we have recharge from the beginning. That's what you see in all the galleries that are still open for you to walk in. We have historic documents of inrush of thermal waters at different levels, which we can also then relate to our temperature depth profiles. We have potentially cold water inrush from other parts of the mine. So we can use these then segmentations together with our mine mappings, or for example, sociological maps, to understand better and more quantitatively how the hydraulics in the mine actually working. And part of what we're doing at the moment is then ground truthing, so kind of find out which hydraulic connections are really open, really there. We're using some underwater drones within the shafts, or cameras within the shafts to identify which pathways might actually be open or not. But now this is the more advanced step once you did the simple temperature profiling. So to coming to an end, I think we all agree that temperature profiles can be a very, very helpful tool. And I just encourage you to play around with our code. The code and the data itself is published, so all the algorithmic details you can find in the respective publication. And the code is on GitHub with some exemplary data. So feel free to try it out yourself. And if there are any questions, I'm very happy to answer them.